Take it away.
Let me know, could you just let me know if you can see it again?
Yes, it's perfect.
Great, thanks. My name is Chuck. I'm from the University of Texas at Austin. And today I'm going to be discussing with you how you can perform integrated data acquisition using Python. So first, I'd like to explain what exactly I mean by integrated. So in this talk, I'm going to demonstrate how you can control and operate a test bench. So in many lab setups, you'll have a power supply, a clock, an amplifier, test board or two, whatever. And maybe you're like me and your back hurts when you sit on a lab stool for too long and you would rather control this remotely. Or if there was some, I don't know, crazy event like a global pandemic and you can't go to the office, it might be nice to actually be able to control this remotely. So secondly, I'll demonstrate how you can communicate with a board to capture data using no closed source, difficult to use manufacturer libraries, but just simple read-write Pythonic type interactions. Thirdly, I'll demonstrate just how to make a user-friendly interface for all this for people who might not have programming experience or might not be comfortable with scripting. And then finally, I'll discuss how we've seamlessly integrated this into our analysis system. Okay, so I'm going to take 60 seconds just to provide you with all the background physics information that you need to know. It's nothing to do with programming, but just explains where we're coming from. All right, here we go. This is the one component of ATLAS. It's called the liquid argon calorimeter. As particles pass through, they deposit energy, and the electrons digitize this data to be saved off detector. So for various reasons, the electronics need to be replaced before the next run of the LHC, or rather the high luminosity LHC run. And to meet all our physics goals, we need a high speed, wide range analog to digital converter, or ADC, that works in some kind of high radiation environment. Unsurprisingly, this is not easy to do and no commercial option exists. So we're developing the chip. Atlas is developing the custom chip. Okay. So let's go through all the players in the show. We're currently on the third iteration of the chip, which is nicknamed Coluda. So what you see here is a test board. Starting on the right, we input a signal that goes to the ADC on the right-hand side of the board. On the left-hand side, we have an FPGA, which controls everything, a clock, power supply, and a way to communicate with the computer, which is through USB. Okay. And then we have the whole stage. So you see 5 of these boards laid out on the table. And then going around clockwise, you see that there's a computer in the center, power supply, signal generator, and clock generator. Okay. And all of these devices we're going to try to control using with Python. Okay, so everything I'll show you today will take place on this bench. All right, I begin our discussion with the topic of instrument control. So all of our devices, as well as most commercial devices on the market, offer some kind of digital communication through TCP, GPIB, or some other common standard. And there are a number of use cases for this. Some of those I mentioned before, but maybe a more serious use of this would be to automate your testing. So this ADC or whatever chip you're trying to test operates on a large voltage range, or it's supposed to work on some voltage range, and you want to gauge its performance across this entire range. You could sit in a lab and manually tune your signal generator and save its result, or you can just program your signal generator to scan through an array of voltages. Okay? So let's work through a demonstration of this. What I'm going to do is connect to the signal generator using a Python library called PyVisa. Physically, the device is connected to the computer with an Ethernet cable. And we're going to do 4 things. First, we're going to connect to the device with PyVisa over TCP. We're going to read out its current state. We're going to try to change the input voltage and the frequency. And then we're going to verify that those changes were made. Now, I have something to admit here, which is that these boards are actively being used and tested by the engineers. And besides, lab access is a little bit restricted at this time, so I won't be able to do any live demos. But I did pre-record videos of everything I would do if they were available, and demonstrated everything there. So I tried to make the screen resolution work for everything. Hopefully it'll be okay. Okay, so to begin, just import this PyVisa library and set up an instance of this resource manager. Okay? So one of the functions that comes with this class basically just lists out all of the resources that you have access to, okay? And that list is shown here. We're going to pick out one, this TCP object to open up. I use this research manager and plug in this this ID and open an instance of it. Now comes the great part about using Python is that you can just use simple commands which are read, and then you read whatever the device has to say, or write, and you pass it a message inside as an argument. Okay? In this case, I'm actually using a thing called query, which is just a fancy function which writes the command that you say and immediately reads back whatever the device has to say. So this ID question mark is a useful command, and we're going to do that. So we see that this is an Agilent 3321, which happens to be the signal generator that sits on our bench. Okay? Not only can it tell us what it is, but it can tell us the current state of things. So again, I'm going to query for the frequency and the, oops. Let's try that again. I'm going to ask for the frequency and the current voltage. And we see that we're running at 2,000 kilohertz, 2 kilohertz and 0.2 volts. Now we can do more than just look at these settings. We can actually change them. So let's try changing it to 1 kilohertz and 0.1 volts. I'm going to use this time a write command and use the apply method. And I just wrote that to the board. So my mouse keeps missing. Here we go. Okay, so I write this again to the board. And now if we were actually sitting in the lab, we would hear a faint click as the signal generator changes its settings. And the little LCD screen on the front of the device would now read 1 kilohertz and 0.1 volts. You don't have to take my word for it because we can just query the frequency and the voltage again, which I do here. Same commands as above. And we see that the frequency is now 1 kilohertz and 0.1 volts as we expected. So this works not only for TCP connections over the Ethernet cable, but also works for GPIP. So we're going to use the same first steps. Going back to our list of available resources, I see this GPIB1 instrument here. I'm going to open a new instance of that resource and query its ID. You see that's Hewlett-Packard. This is our power supply. These things are actually, this power supply is hooked up to more than one board at the time, and I didn't want to kill the power for all 5 boards at the same time. So I'm not going to actually turn it off and back on, even though we could. But I'll just query what the output is, and it tells me that it's currently on, which is great. Returns true. Sometimes the manufacturer will actually have a Python library built for you, and it can be simpler to use that. And so I wrote out a quick example of that here. In the case of our multimeter is connected to a resistor which measures the temperature of the chip and its at the current time. And the manufacturer has actually been kind enough to write some scripts to completely automate that procedure. Okay, so you can go download these scripts from online, and you have, or write one yourself, and we have a command to reset the multimeter. That's this first file of commands here. And then there's another one which gets the resistance of the multimeter. Okay. And then I'm going to do that 10 times, run that script 10 times over. And then finally we'll print out the readings that it obtained. So you see that it's read out 1130 ohms. The measurements are in ohms, but you can look up in a table and convert this to Celsius if you desire. we've never bothered to do that. One funny thing is that Keysight software has a known bug where the first measurement is always wrong. So we just ignore that, and we see that the other 9 are very consistent. Okay. So to summarize, in the demo, you saw me check the status of the power supply, which sits on the test bench. This was done with GPIB. And additionally, I demonstrated taking readings from the temperature sensor that's glued onto the exterior of the chip, and that's a picture of that here. So this is the temperature sensor that we just measured. All right, so the idea of taking measurements leads me right into the next component of our integration, and that's reading in data. So there is a module called PySerial, which allows the developer to communicate with a USB chip. The package works on any operating system, and will actually automatically choose whatever backend you need for whatever operating system you're currently using. And that's a really great way to make your program completely platform independent. As a quick aside, why does that matter? A little backstory. We have like 5 to 8 of these boards, and we'd like to test them all. So you need 5 to 8 computers. And being mostly physicists, we only had non-Linux machines, and the old software that we used was dependent on these libraries, which only used Windows. So all of the computers we were using to test this were very old, and meant we were testing boards one at a time. Now we can throw any old computer that we have hooked up to a board and run all the tests in parallel. So by choosing to make my platform or my program platform independent, which is generally an easy task with Python, I was able to vastly improve our efficiency of data taking. Just something to think about when you're starting a project that involves data acquisition. Anyway, the main selling point of PySerial is that all of this backend nonsense is made entirely transparent to the developer. So the API calls are simple file-like access functions. Just like before, we're going to write a message to the chip, call a function called write, and put your message in as an argument. And you want to read its response, just use read. Our board happens to use this particular USB chip. In the past, I've used a non-Python system, which meant hours of installing random drivers. But there's no need for this when you have PySerial. So to introduce you to the program, we're going to I'll show a couple of screenshots of what we do. One of the key functions of PySerial is just to list the ports that it has access to. Okay? So I have a screenshot of doing that on the computer here. And we see that there's some device on COM1, and there's another device which is operating on COMs 17 and 18. That's our dual channel USB chip. Okay. And then here I have an example of what this looks like to the developer. All you do is, all the developer sees is that third line, a simple call to write and then your message. So PySerial supports a number of different message formats. We chose to use byte arrays, but you can choose whatever you like. And I just included some of the lines around that write command to show some of the context. We don't want these write operations to basically interfere with any other operations that are that the program is doing. So we do this on background on separate threads, and I just added some mutexing around the write operations to prevent trying to write to a single channel from multiple threads at the same time. But really, all you need to know is this third line. It's your port object, which is this thing called FIFO.write, and then you pass it your message. So what does that operation, what does that write operation look like on the hardware? And that's what we'll do here. Okay. So on the board, the FPGA is your supreme leader. The FPGA and the computer don't communicate directly, but pass messages to one another through a messenger, this USB chip. So as a developer, you're only communicating with the USB chip directly. That's what PySerial is doing. You can think of the USB chip as just 2 buckets, bucket A and bucket B. So the computer puts some 6-byte message into bucket B, the FPGA picks that message up, and whatever command it specifies, the FPGA performs that action. So the command could be, for example, to pick up the settings which the computer has left in bucket A and apply them. Or the command could be to take and store data. So that's the example we'll look at here that I've printed out on this screen. So let's break this down command by command. I've called 3 instances of write and 1 instance of PySerial's read function. So the first one is PySerial write, and that command corresponds to telling the FPGA to listen. The second line is a write command, which tells the FPGA to take 1024 data points. The third write command is to say, move that data that you just took into bucket A. And then finally, I call a read command on bucket A, and then PySerial starts spitting out data. And that's it from the user's perspective. That's all you see. So with that, we'll move on to the next element of the integration is the user interface. So there's been a number of demos on this at the conference already, and I've shortened this part a bit. All of the modules that have been discussed so far are all usable in API format for someone to write a script. But when you're developing a large program like this one, you'll find that many of the people you're working with have little to no software experience, and nor should they. The engineers, design this chip should focus on their specialty. So what I did was tie everything together with this easy-to-use UX, which I designed in PyQt5. Just to give a brief walkthrough, on the left hand, this is the home page of the user interface. On the left side, we have the serial connections. This is how we actually open up to start talking to the chip. We have different tabs which control all of the settings of our ADC. Some easy buttons to just take data or some simple actions. So for example, this orange button that I'm hovering over, this is the button which I pressed to execute those 3 write commands and 1 read command that you saw on a previous slide. We just have the options about how to store your data, which we'll go through in a second, and then some immediate display of the data that we've taken. So just like PySerial abstracts away all the complicated nature of digital communication and provides the developer just a read and write function, things like using PyQt5 to create things like checkboxes, drop-down menus, text box entries, they abstract all the way the low-level operations of the PySerial for the engineer who's testing the chip and allows easy interaction. They don't have to know how to use PySerial even. Okay. And the last major integration element to cover is the data analysis. So generally, it's desirable to perform analyses in multiple stages. Just like when we're taking data at the LHC, we want one is rapid feedback to the experimenter during data taking. So usually this is just simple sanity checks. And 2, we want an organized processing of data for later analysis. And what I'd like to argue is that you can do both of these things if you integrate all of your data acquisition with Python. So going back to the GUI page from a moment ago, you'll see that there's a small checkbox labeled FFT. So one of the ways to measure the performance of a chip is to apply a sine wave and take the Fourier transform. In the old version of the software, it was a huge pain to do this, but now it's as simple as calling, once we switch to Python, now it's as simple as calling scipy.fft and just plotting results. And look, wow, there it is. Cool. So as a side note, if this FFT looks weird, it's because the board set up to do a different kind of test, not the one where the FFT matters, but hey, it's a plot. Right. Key point there is just it's easy to integrate simple analysis techniques like scipy functions if you integrate everything together. Another feature we implemented was use of matplotlib features. So when you're taking data for long periods of time, it makes sense to have continually updating plots, and you can monitor the status of the data taking in real time. And I linked to the implementation that I made for using matplotlib and PyQt to make dynamic plots. And I also just made a quick video, which I've sped up a factor of 30 times, which just shows the chip doing its operations and humming along while we watch the plots generate. You can also do cool things like in the top left, where it only shows the last 25 data points, and it's just continually adding a new one on the right and chopping one off on the left. And this is pretty straightforward with this implementation that I've mentioned. So when it comes to long-term analysis, data format matters. Different tasks call for different tools. So if you're analyzing a complicated collider physics event with many particles and many properties for each particle, you might need something like root or uproot, awkward, whatever you, however you interact with this. But for simple data streams like this, just one or a few streams of numbers, root's a bit of a sledgehammer solution. So if you haven't heard of it, I'd like to introduce you to one possible lightweight solution used by collaborations like LIGO. It's called HDF5. And that's how we've implemented our data storage. The acronym stands for hierarchical data format. And that works well for us because we'd like to keep data separated by each test. And by each channel, we have multiple channels on this chip. And we'd like to separate each data by channel. So we'd like some kind of data structure, which looks like this. We have a test and 2 devices, and each device has its associated data. Then we take a new test, and we'd like to make a new set with that. Sadly, there's just no way to integrate Python with HDF5. Just kidding. It's easy. There's a package for that. It's H5Py. And it's user-friendly. And you can read and write files like you would any other file. And you can access the hierarchy in a Python dictionary way. It's really quite convenient. So for that, I just included a quick demo if you haven't experienced HDF5. So I'll import this library here. I have one of our data files from this chip that I took earlier this week on the web. If you'd like to try it out yourself, I've already downloaded it. So we'll go ahead and skip to the next step. And you can do things like, you can see that F then behaves like a Python dictionary. So I can print out whatever the keys are. And then let's see if we go to, we'll actually just maybe take a look at just the first level of this. We see that it's another HDF5 group. So again, this is another dictionary, Python dictionary-like object, and we can print out the keys from that. I went ahead and done all the rest for us, gone all down the layers, pulled out the raw data. We see that it's just a 1024 by 16 element array. And that's what it looks like. These are actually the actual bits that we took when I took the data. And now I can plot those. So you may recognize this plot from the image, the screen cap of the GUI that I showed before. We can easily recreate this plot offline long after having taken the data. But it's really easy to navigate through all of your measurements. So I put that on the, I put that notebook on the Indico page if anybody wants to try it out later, but there's lots of great, more detailed tutorials of HDF5 on the web. Okay. So in conclusion, with Python, you can really have everything you need in one program. PyVisa and custom manufacturer-built Python packages allow you to control your test bench. You can communicate with your test board using PySerial. You can build a user interface with PyQt, and you can analyze your data in real time with packages like SciPy, Matplotlib, and store it for later using H5Py. So if I were to sum up this talk in a single phrase, it would be this. Don't write any code for yourself, never. Someone's already probably written it for you. Just get a great package manager like Conda and stitch a bunch of things together. And yeah, your import list might look like this, but who cares? You didn't have to write any code, and that's great. So with that, I will take any questions that you may have.
Great, thank you. I saw that there were some up. Maybe I should share this, the questions?
Yeah, please.
I don't remember how to put into presentation mode. But...
I can do it, Jim.
Oh, you can do it? Oh, is this,
yeah, here.
I was just gonna zoom it up, but okay.
Let me just, since you're already sharing, just can you click that link?
Oh, he's not sharing anymore.
Oh, okay. Well, then I will do this. He said, give me a second. Okay. Right. So let's take this. Hopefully people can see. Let's take this first one from Gordon. So LabVIEW is a common automation tool in the space. How would you compare these two?
We actually used to use LabVIEW. Before we were able to integrate all this programming into one. One of the engineers that was designing the chip wrote his own custom LabVIEW program. He's now actually switched over to writing scripts that integrate well with this Python package. So yeah, we've used it, but just for the sake of making everything work in one single program, we have basically given up on that. But yeah, it does all the same sorts of things that LabVIEW does.
Okay. All right, and next we have from JF, we have, does PyVisa still need National Instrument specific equipment or drivers?
I think not. I never actually pay careful attention what's happening when I like Conda install PyVisa. So there may be some package that NI has written and put on Conda that I'm not seeing happen. But no, when we're using, at least this is true for Linux devices, we were able to do this without going on any website and downloading drivers. It just all worked straight away.
Nice. That's always a pleasant experience.
Yeah.
Okay, and then I think we're still good on time, right, Jim? So just out of pure curiosity, what's under the, I can't touch this tab.
Yeah, that is the button to, on that page is the button to turn off and back on the power supply.
Okay.
Yeah, so it's, because you just have to keep in mind, and there's a little warning on that page too that says something like, just because you can doesn't mean you should. Because it's a reminder that if you hit that button, you will be killing all of the boards, not just the one that you happen to be connected to right now.
Yes, yeah. Okay, and then we also have, let's just take these last two. So from Jim, we have the ADC circuit board has 12 inches of straight lines. I suppose it comes in standard size and you didn't need all that space?
Great question. Why is that test board so long? The reason for that test board being long isn't not an accident. We have smaller boards that are used for the lab benches. What we call these long ones are the radiation boards. So to make sure that this thing is actually radiation hard and will last the entire lifetime of the HLLHC, we pack them all up, ship them up to Boston, and go to Mass General and put them in a proton beam that they have for cancer therapy. On the weekends, beam doubles as a science experiment, and research groups can book time with the beam and put their electronics or whatever they want to irradiate in a back room off of the cancer ward, and you can irradiate your chip. So we basically just blast it with a full HLLHC lifetime of proton radiation, and see if the performance of the chip degrades after it's been heavily irradiated. Okay, so to get back to why the length, you just want to irradiate the chip, all of the other FPGA USB controller things. Those are not radiation hard. So we put everything on the right-hand side of the, or whatever side of the board it is. The far one side of the board is covered by lead bricks, and we just expose the ADC itself. So that's the only thing that gets irradiated.
And then a final question from JF. How did you design the PyQt or PyQt interface? Write PyQt code directly, or use those Qt design IDEs, or maybe even write QML?
I use the IDEs. It's just a drag and drop. If you've never, for those who may have not done this before, it's just a program you can open up and drag all your click boxes and your text entry and buttons into place. And then all of the visual code is generated for you automatically.
Okay. We have in chat at least one mention of a final question. So if that person wants to be very quick, we can go ahead and get that in.
So I noticed that you were working with it looked like at some point you were working with an oscilloscope in this. Is that right?
Yes.
Yeah. So in that case, what sort of tooling did you find out there in the wider community for well, dealing with the fact that all these oscilloscopes have different kind of idiomatic codes for interacting with them? Or have you ever used the GPIB over Ethernet protocols where there are all these various weird scope-specific languages that you have to interact with?
So we didn't actually use the oscilloscope, as far as I know, for any data taking purposes. Okay. That was more for debugging.
Gotcha. Oh, right. You're working with the kind of final design-ish ASICs, more or less, right?
Yeah. So.
Yeah, the perspective I'm coming from is very early stage design ASICs, and we're actually recording data with the oscilloscope. So that's why I was curious to ask.
You can do that. We actually had, in one of our previous iterations, an ASIC, tying back into the first question, we had an ASIC which didn't have the software capable of taking data from it. Mm-hmm. So one of the engineers hooked the ASIC up to an oscilloscope, which then was hooked up to an NI Instruments LabVIEW type interface, and he wrote some programs to use the oscilloscope to take data.
I see. Yeah,
that was a while ago.
Now we're getting pretty long here, and apparently there's the photo coming up. But it would be interesting to catch you offline to talk about directly interfacing Python to oscilloscopes and stuff like that, and DAQ related matters in that side of things, if you're interested.
Yeah, feel free. I'll meet you on Slack at some point.
Yeah, I was going to suggest Slack. That'd be perfect.
Okay, well, thanks very much for that talk. It was personally I thought super cool. So very glad that we got